Ever wondered how a simple puff of steam can move a 1,000-ton train? It seems like magic, but it's actually a clever trick of physics. Welcome back to Master the Chaos. Today we're looking at heat engines, the machines that quite literally built the modern world. At its heart, a heat engine is a device that turns thermal energy, the chaotic jiggling of atoms, into organized mechanical work. To do this, it needs a temperature difference. It takes heat from a hot source, uses some of it to do work, and dumps the rest into a cold sink. Let's start with the classic, the steam engine. It begins with boiling water. The heat from coal creates high-pressure steam. That steam is packed with kinetic energy. As it expands, it hits the piston with incredible force, pushing it forward. This is chaos turned into a straight line. The engine's mechanics then convert that linear push into rotation. Suddenly, the chaotic energy of fire is turning a wheel, a propeller, or a factory belt. But what about the car you drive? That's an internal combustion engine. Same principle, but we put the fire right inside the cylinder. It's a 4-act play. Act 1, intake. The piston drops, sucking in a precise mixture of air and gasoline vapor, cool and ready. Act 2, compression. The piston rises, squeezing that mixture. As we learned in Lesson 4, when you compress a gas, its temperature and pressure skyrocket. Act 3, power. The spark plug ignites the gas. The explosion creates massive pressure, driving the piston down and turning the wheels. This is the work phase. Finally, Act 4, exhaust. The piston rises again, pushing out the spent gases to make room for a fresh breath. And the cycle repeats thousands of times a minute. Now here's the catch. Why can't we use all that heat for work? Why do cars need radiators, and why do steam engines puff out hot clouds? Because of the second law of thermodynamics. You can never turn 100% of heat into work. Some energy must be wasted. It's the universe's tax on motion. Sadi Carnot, a French engineer, realized this in 1824. He designed a theoretical perfect engine to find the absolute limit of efficiency. The Carnot limit tells us that efficiency depends on the temperature difference. The hotter the source and the colder the sink, the more work you can extract. This is why power plants use superheated steam and giant cooling towers. They are trying to maximize that gap to squeeze out every drop of electricity. In a turbine, we don't use pistons. We use the steam to spin blades directly, like a high-tech windmill. It's more efficient, but the rule remains the same. That shimmering air from your exhaust, that's energy that could have moved your car, but instead, it's just warming up the atmosphere. It's inevitable. To get work out, heat must flow, and flow requires a destination. If the whole universe was the same temperature, no work could ever be done again. So, heat engines are our way of catching energy as it slides down the temperature hill. We intercept the chaos and force it to do something useful. From the first steam pump to the rockets taking us to Mars, we are all just trying to master the chaos of heat. In our next lesson, we'll look at the machines that do the opposite. Refrigerators. How do we make things cold when the universe wants them hot? Make sure to subscribe to James's Physics 101 so you don't miss Lesson 7. We're almost through the laws of the universe. Check out the full Master the Chaos playlist to catch up on anything you missed. Keep questioning, and I'll see you in the next one. Thanks for watching James's Physics 101. Master the Chaos, one lesson at a time.